All right, so the next thing we're going to look at is hybridization theory. Don't forget, now that we've gone through the answers, to make sure that you have looked at all of your exam reflection, because I'm going to collect that at the end of class. So if you have more thoughts to put down, feel free to do that as I'm getting set up here. Okay, so I'm quickly going to go over what we've already looked at as far as bonding theory, and then I'm going to start talking about molecular orbital theory. So remember on Wednesday, I said everything that we've been looking at, all these different theories sort of build on one another and enhance one another and work really well together. So there's nothing about valence bond theory that really contradicts VSEPR theory. It just sort of enhances it. What we're doing now is really kind of a weird left-hand turn, getting off the railroad tracks, and now we're on a bus. And it still explains bonding, but it does it in a completely different way. So let's look at what we already know. Remember that we've talked about sigma and pi bonding. So when we have a sigma bond, the electrons are between the two nuclei, the internuclear axis. So what kinds of orbitals can make sigma bonds? All of them. Any kind of orbital can make a sigma bond. It just has to have the part that's sticking out overlap with the part that's sticking out on another orbital. So it can be a hybrid, it can be S, it can be a P, they all sigma bond. The key thing is the electrons are in between the two nuclei on that line. Now, every bond has a sigma bond as part of it. If it is a single bond, it is only a sigma bond. But if it is a double or a triple bond, it's going to have a sigma and also one or two pi's. Okay, so if I were to ask you which of these bonds has some sigma bond character to it, you're going to say all of them because they all do. Okay. So we had this chart that we really want to connect how many things we're attached to the type of hybridization, to the bond angle. So one really good thing to remember is that if I only have single bonds, because we're only going to be dealing with things that are that follow the octet rule. If I only have single bonds, it's going to be sp3 hybridized. Okay, so if I have a nitrogen with 3 single bonds, sp3 hybridized. If I have an oxygen with 2 single bonds, sp3 hybridized. A carbon with 4 single bonds, sp3 hybridized. Okay. If I have any double bonds, that's when I start looking at the other two. Okay. Don't forget that lone pairs have to be in an orbital too. So when you're counting how many orbitals you need to make, how many hybrid orbitals, we have to count them for the lone pair. So in this case, we have NH3. It has the, it has the 3 hydrogens, but it also has a lone pair. So we have to stick a pair of electrons into an orbital. So we have to have an orbital for that. Same thing for water. The oxygen needs hybrid orbitals for those. Okay, so let's take a look at an example. We're going to look at the carbon furthest to the left, the one with a triple bond to the nitrogen. Now, remember, if we want to know what the hybridization is, our first question is, how many electron domains are there? So how many electron domains on that carbon? 3. I'm sorry, not 3, 2 of them, just 2. Okay, it is a triple bond, but there's only 2 domains. One domain is a triple bond and one is a single bond. Okay, so unlike with formal charges, we counted each of those lines separately. When we're looking at hybridization, we're just counting that whole group as one. Why? Because they can't get away from one another. I can't change the geometry by splitting up those bonds and moving them around, because if I did, the nitrogen wouldn't know which way to go. Okay, so only 2 domains. So I need 2 hybrid orbitals. So if I have 2 hybrid orbitals, what is the hybridization? SP. Always got to start with S, and then I add as many P's as I need to finish it out. So this is SP hybridized. Okay. Is the nitrogen also SP hybridized? How many electron domains does the nitrogen have? 2. So it's also sp hybridized. It's just using one of them for a lone pair instead of for a bond. Okay, now let's look at this ring, and we're going to talk about the ring a little bit more after this slide. Any one of those carbons has the same hybridization. What would that hybridization be? sp2. So sp2, because each of those carbons has 3 bonding regions and no lone pairs. Okay. Now, the other thing I might ask you about these is, what is the bond angle? So on the ring, what's the bond angle? 120. Now, it's probably not exactly 120, but we're just going to go with the ideals. We're not going to worry about less than or equal to or whatever. We're just going to say it's 120. What about the carbon furthest to the left, the one with the triple bond? What's the angle on that? We said it was sp hybridized. sp hybridized, it has 2 bonding domains, no lone pairs, 180. It's going to be linear, right? Okay, now those both kind of look like that in the picture. Now let's look to the carbon that's furthest to the right. So it's attached to 2 oxygens right here. Okay, so what's the hybridization on that? It's got 3 bonding regions, no lone pairs, so it's going to be sp2. Okay. And so being sp2, what is this bond angle going from the carbon to the oxygen? What's that bond angle? 120. It doesn't look like 120 in the picture. Now, is the bond angle going from the oxygen to the carbon to the oxygen also the same? Yeah, it's also about 120. It's probably not exactly the same, but it's going to be pretty close to 120. Okay, so the Lewis dot structure does not show you the geometry necessarily. Sometimes we try to approximate it, but sometimes it's just simpler to write things out like this because molecules are 3-dimensional. They bend and twist all over the place. Okay. So we talked sigma bonds. Pi bonds happen when we have leftover p orbitals, and those p orbitals can overlap. So the things to remember with that is that the overlap is above and below the internuclear axis. It's not on the internuclear axis. So this is showing 1 sigma bond and 1 pi bond. Now, even though I have a top and a bottom to that, it's like a hot dog bun. The hot dog bun has a top and a bottom, or a side and a side, but it's just 1 bun. This is just 1 pi orbital. Pi bond. Sorry, pi orbitals are coming next. And this is 1 sigma bond. Now, sometimes we ask the question, which bonds have pi bond character? So I'm going to go back to the previous slide. Everywhere we see multiple bonds, so the triple bonded carbon, the double bonds on the ring, the double bond carbon to the oxygen, all of those have pi bond character. But when we have resonance, we can also have pi bond character in something that looks like a single bond. So if we look at our ring there, I could have easily drawn this structure where the bottom 2 carbons were double bonded and the ones to the side of it were single bonded. And then the top side ones were double bonded and the top one was single bond. So I could have just rotated where I have those double bonds. And in reality, what ends up happening is that each of those carbons has a p orbital sticking up on it. And they're all equidistance apart. And so instead of the electrons just staying between 2 atoms forming 1 pi bond there, you kind of spin around the whole thing. It's a particularly stable arrangement, which is why we see that shape in a lot of organic molecules. And so that means that even though I have lines there that look like only single bonds, they have some pi bond character. So whenever there is resonance, the single bonds that could be double bonds are going to have pi bond character. All right, reminder that triple bonds is just a pair of pi bonds. So instead of having just the ones top and bottom, we also have one in and out. Otherwise, they're the same. Remember that the pi bonds have less overlap because they're not pointed at each other. They're just coming up side to side. And so because they're coming up side to side, that's a weaker bond. Okay, so we don't get as much energy, not as much stabilization out of that. Remember, we also learned on Wednesday that this can keep us from rotating around the molecule, whether it's a double bond or a triple bond. If we were to rotate, it would break those pi bonds. So this stabilizes the molecule so it doesn't rotate. All right, and so this is illustrating the resonance, and the kind of hexagon in the middle, that's that ring structure that we were just looking at. And so you can sort of see the p orbitals here forming the pi bonds. But the pi bonds go all the way around. Instead of just having 3 individual pi bonds, everywhere we have 2 p orbitals that are both pointed in parallel to one another, we end up with pi bond character. Similarly over here with the ozone. Normally we draw ozone with, I erased it, 1 double bond and 1 single bond. But since it can resonate to both sides, there are p orbitals sticking up on all of those. And that means that they're all sharing it. So that's called delocalization. Localization is when they stay between 2 atoms or in a lone pair. Delocalization is when those electrons can move around. So these electrons can just spin around this thing all day. They don't have to stay on 1 carbon or between 2 carbons. Okay. So that all is what we've talked about with valence bond theory. That's the bulk of the stuff for your quiz for Monday. But I'm going to have a little bit on molecular orbital theory. Oh, gosh, we're running out of time. So we are just going to introduce this. I'm going to go through this part really quick because this is just reviewing what we said before. Vesper theory spreads out our electron pairs, but it doesn't correlate to the atomic orbitals. So we needed something that had atomic orbitals involved. So valence bond theory said, okay, let's make hybrid orbitals out of those atomic orbitals, okay? Now this is on Canvas, so if you can't get this all written down or want to go back and look at it, you can. All right, so this enables us to talk about the shapes, even though the atomic orbitals have different bond angles or different angles. What these models don't do is they don't explain paramagnetism. Now, we just barely touched on paramagnetism in my class last semester, and from my previous class, it sounded like Dr. Hamilton didn't get into it a lot either. Does anybody know what causes paramagnetism? Anyone who can read can figure it out because I put it here. Paramagnetism comes from unpaired electrons. Now, we have seen one source of unpaired electrons before. So we said that exceptions to the octet rule are electron deficiency, hypervalency, and what was the third one? Free radical. That's when we have an odd number of electrons. And that works fine for dot structures. We show up with an odd number of electrons. We say, hey, it's unpaired, it's paramagnetic, not a problem. But there are some molecules that are stable molecules. So free radicals, we said, we're not stable. There are some stable molecules that are paramagnetic that a dot structure would make it look like they have all their electrons paired. They have an even number of electrons, yet they're still paramagnetic. So this is one of the things that molecular orbital theory is going to help us fix. The other thing it's going to help us fix is, remember that I've been talking earlier in the week that valence bond theory works great for our organic carbon, nitrogen, oxygen, things that follow the octet rule. But the heavier elements and the metals, I'm like, it doesn't work for this. We can't explain it with this. So they do something else. Molecular orbital theory works for all of these. So why don't we use it for everything? It is freaking complicated. Okay, so the orbitals predicted by valence bond theory are predicted to be localized, meaning that the electrons are either going to be in a lone pair or they're going to be between 2 atoms. They're not going to wander around. So we don't really deal with resonance very well with valence bond theory. We understand that it happens, but there's no particular kind of orbital that says this is a resonant orbital. And so molecular orbital theory is going to help us deal with resonance. Okay, so for your quiz, you should know why we need molecular orbital theory. I'll probably ask you about those two things. It explains paramagnetism and explains resonance. Now, we don't know why it explains it yet. We'll get to that on Monday. Now, the idea of a molecular orbital is that instead of taking orbitals, atomic orbitals on one atom and mixing them, we're going to say, you know, that atom doesn't know what shape it's going to take on. It doesn't know whether it's going to be tetrahedral or whatever. So why would it know what hybridization to do? But if two atoms come together, depending on how they come together, their atomic orbitals can overlap. And so that overlap of those atomic orbitals is going to help us come up with a molecular orbital. All right, so the atomic orbitals on different nuclei are going to overlap to form molecular orbitals. If they're on the same nuclei, that's valence bond theory. On different nuclei, it's going to be molecular orbitals. And we have that same conservation of orbitals. However many orbitals we start with, however many atomic orbitals, that's how many molecular orbitals we're going to get. We did the same thing with hybridization. We started with an S and 3 Ps. We ended up with 4 sp3 orbitals. Here, if we start with 2 s orbitals, we're going to end up with 2 molecular orbitals. And we will talk about what those orbitals are on Monday. All right, have a good weekend. Please turn in your exam reflection up here, and I'm going to go grab that other one from my office. Did anybody else miss Wednesday? So you need one as well? Oh, you printed yours out. Okay.
No, I just wrote it down.
Oh, you just wrote it down. That's fine.